Hello and welcome to the LUniverse Virtual Planetarium from Lancaster University. The following is a recording of one of our free live public shows that we ran during early 2021. I hope you enjoy. Before I go on all about how today is going to work, I must start by introducing our team here today. So first of all, behind the scenes, working diligently are Pascal. Hey, hi Pascal. Who will be doing a fantastic job of doing some research behind the scenes, as well as answering your questions, as well as Diego, who is here as well. Hey, Diego, who will be doing the same thing as Pascal. We diligently working behind the scenes to answer questions, handle all your Q&As. And with me as a special guest today, we also have Josh.
Hey, everyone.
Hey, Josh. Hey, Josh. Josh, would you like to introduce yourself?
Yeah, of course. Thanks for letting me, Andrew. So my name's Josh Wiggs. I am a PhD student here at Lancaster University, working over in the Space and Planetary Physics department, mainly looking at stuff around Jupiter.
Brilliant. Thanks ever so much, Josh. So what's going on here? What's all this about? So this week we've realized over the last I think now 7 weeks of shows, you have been sending in some fantastic questions to us, some really cool what we call hypotheticals. So just like what if questions, what if statements, like what if sun becomes a black hole, what happens if galaxies collide, all these fantastic questions. And we wanted a really fun way to show you the answers, not just to show you what a scientific discussion looks like, but also a nice visualization of those questions as well. And that's what Josh and I are going to be trying to do today. So we're going to be sitting here having a chat about physics, trying to figure out how these things can work. And as we have that chat, I'm going to live, desperately behind the scenes, scramble to put a simulation together to show you somewhat what would happen as those hypotheticals play out. This has not been attempted before. At all. I have no idea how this is going to go, but I'm really excited to try. And it's a nice way, we hope, for you guys to see what a genuine physics discussion is like. Because if you ever sit in a pub with a bunch of physicists, you'll realize all we do is sit there and go, what happens if this? Hang on, what's that again? And then we just sit and try and figure it out. The term is normally called back of the envelope calculations as well, where we just sit and try and jot and work it out. Okay, with all of that faff out of the way, I think it's time to try our very first question. So this is one of the ones that I've been wanting to chat about for a little while. Again, this has not been prepped. Josh doesn't know what's coming up. We're just going to have a little chat about it and hope for the best. I think let's start, Josh, with what happens if two galaxies collide? What happens if two galaxies collide? So what on earth do we think happens?
So I guess when talking about this, it makes sense to talk about something which is going to be coming up in, I say, the near history of our galaxy. When I say near history, I mean in astronomical terms. So not within any of our lifetimes, that's for sure. But that will be the collision between our galaxy, the Milky Way, and the Andromeda Galaxy.
Oh, yes.
So the Andromeda Galaxy and the Milky Way Galaxy are hurtling together. I think it's like 3 kilometers, something like 300 kilometers every year or something like that. And there's a lot of distance still to cover. So like I say, definitely not going to happen in our lifetime. So nothing that anyone needs to worry about. So I guess what I'm saying by this is that this does happen, and this will eventually happen to us. And it's something that we can, if we look out in the night sky, looking at the history of the universe around us, it's something that we can actually observe happening.
Yeah.
So it's something that we do actually have a fairly good idea what's going to happen. I think the thing that
yeah.
Go on, Andrew, you jump in.
I was just to say, I think you make a really good point there, Josh. I think it's something that we have a vague notion of, and I think it's something that it's actually quite common. Galaxies collide all the time, right? And it's these collisions that cause us to change from spiral galaxies typically over to elliptical galaxies as well.
Yeah, definitely. And yeah, the amazing thing is that just by looking up in the night sky, using some of the more powerful telescopes, Hubble being an example that springs to mind, we can watch galaxies colliding, not all the time, but we can find examples of it. And excitingly, we can find examples of it over when galaxies are in different stages of colliding. So we don't just have to look, these don't happen in seconds. These happen on astronomical timescales. which is many millions of years realistically. So it's something that we can look at in all different stages.
Yeah, absolutely. I mean, I've managed to throw a simulation together here. I say throw a simulation. This is part of Universe Sandbox. There's a package, and there's one that's already built in. I'm just going to pause it before they start to collide. So this is showing, I believe it's the Milky Way and Andromeda simulations of, they don't actually look like this. This is just a particle simulation of them colliding over the course of millions of years. So every tick, as in like step in the computer simulation here, is roughly 50,000 years. So this is a really sped up thing. In fact, if I just do that, you can actually see the timescale on the top left there. That's a bit better. Yeah. So this is actually showing what would happen if these two galaxies started colliding. Again, we're talking millions of years of time passing here. But what I think is really interesting to point out, you can already see it, is that obviously this is not a perfect simulation, but a lot of things, although quite messy, are just going to pass through. And they're just going to pass straight through each other, right?
Yeah, I mean, I think people, when they think about these things, they tend to think about galaxies. Galaxies are roughly disc shaped, so we'll talk about two discs. They think about two frisbees colliding, where they'll collide with each other in the air and deflect one another. But when we look at galaxies, the objects in galaxies, so we talk about stars normally when we talk about objects in galaxies, because anything else is just too small to think about. Stars are relatively tenuous in this cloud that we call a galaxy. So there's a lot of room between them. So actually what happens is when these two disks of material start to come together, most of that material actually misses one another, and they tend to, the parts away from the core of a galaxy actually pass through each other relatively easily without any sort of cataclysmic events happening. The more interesting part, of course, happens when the two cores of the galaxy start to collide and those supermassive black holes start to interact with one another. So you can see, maybe Andrew can rewind his simulation a bit. I'm not sure if that's possible. I think he's telling me that it's not. So what you saw anyway was when those two galaxies when the cores of those galaxies started to come together, there was a lot of material all of a sudden thrown away from that interaction, and that's because although the material that makes sort of the disk outside of the core of the galaxies is very tenuous and doesn't interact with each other very much. These two massive black holes in the middle, when they get close to each other, they have a huge gravitational interaction with each other, causing a sort of a shock wave to be sent outwards, which then interacts with the stars, causing all this material to be blown out of galaxies. And you can see there's sort of a cloud of material around the galaxy. But that's not to say that all of the material is blown away. You can see a vast majority of the stars are maintained in a new form, in perhaps a different distribution to they were before, but they are still there. And these two galaxies will eventually settle into an equilibrium and form one super galaxy.
The stars orbiting in elliptical ways around it. That was me messing that up. So I was just saying that you could see there, you got the stars, you got the cores in the center there, the supermassive black holes, and you got all the stars orbiting around them in sort of elliptical shapes, and they're rapidly heading towards each other. You can actually see them drifting slowly like that, and they're going to slowly form a much bigger central core as well. I think it's really interesting to note that for the most part, most stars I think would be okay. You would vaguely keep in something semi-stably resembling an orbit around something, but there's a big variation of what might happen to a couple of the stars. You can really start to see actually this, you've got this quite dense core now as opposed to what it was before.
Yeah, and that dense core will start, that material that was blown away, that dense core will start to reattract that as well, and it will settle back down.
But I think you'd have a flurry of star formation, wouldn't you? You would have, as some of the gas density increases, because you got those, lots of spare gas in both galaxies come together, that increases density. You might be able to form a few new stars from that, but then a lot of them, after a while, you'd actually have a much greater reduction in star formation because you've actually blown so much gas out as well, right?
Yeah, and I think as that resettling process happens, you'll get dust clouds starting to form, forming nebulae, and then those nebulae can become new star-forming regions, starting the rebirth process all over again.
Yeah, absolutely. That's pretty cool. So hopefully we're sort of clocked on to what's going to be going on here. These are the core ideas of us just really exploring some cool physics. Alrighty, let's have a little look. Okay, so we've got here what happens if the sun runs out of fuel to burn and stops burning. That's a really cool question. Josh, you want to chat about that one?
Yeah, can do. So the sun running out of fuel is not going to happen anytime soon.
No, not at all.
by saying that, there's still millions of years left of fuel left. I'm thinking hydrogen and helium, which make up the two main components of a main sequence star. Once they burn out, then the star, being relatively light, will go through a red dwarf process, eventually becoming a white dwarf, and then eventually a black dwarf. Sorry, I'll move on because I thought. So I take it the question is meaning if the star runs out of fuel tomorrow, it disappears completely.
I was thinking more on the lines of like what would happen to our solar system during the phases of the sun's death, basically. Right. Which we can talk about. I think I can actually show what happens if the sun became, well, the next step in the sun's evolution, of course, is red giant. Right? Yeah. So red. Yeah, go ahead.
So a red giant is what our sun will eventually become in millions of years. It's when the lighter elements, the lighter elements being hydrogen and helium, start to form heavier elements. The heavier element being carbon, and what happens is this causes the pressure balance. So that you can think of two. When you think of two things pushing against each other, if they're not moving, they're in a balance essentially. And the two things which are pushing against each other to form the balance in our sun is the gravitational pressure from the sun's own mass, and the gas pressure being caused by that nuclear reaction happening in its center. So that nuclear reaction is pushing loads of energy outwards, and its own mass, the gravitational mass, is pulling it back in. And where those two balance each other is what we see our sun as. So what happens is later on in its life cycle, when it changes what it's burning, like I say, from helium to carbon, is that pressure balance changes, and what happens is the sun starts to expand because the force from the inside is now overcoming the force from the outside, essentially. So the sun starts to swell outwards and forms something called a red giant. The reason the color changes is because as it swells outwards, the surface cools slightly.
So what I've done here, sorry to interrupt you, Josh, this is really cool. So what I've done here in our simulation, this is really fun. So I've made the sun 1.5 AU in diameter. So to clarify, AU is the distance between the Earth and the sun. So 1 AU is that distance. What is it? 1.5 times 10 to the 11 meters.
I think one of our fact
finders can confirm that number for me. I'm fairly confident it's 1.5 times 10 to the 11, but I'm 1 point something. Oh, I don't know. I'm putting it out of nowhere now. But basically, it's a very large number. So what would happen is there's a lot of different predictions to how large the sun would become during its red giant phase. Some suggest it can be up to 1.5 to e to the 1.5 times 10 to the 8 kilometers. It's 1.5 times 10 to the 11 meters. Thank you, Pascal. I'm surprised I've actually had that in my memory somewhere. So there's some predictions that say it's going to get up to 1.5 AU in radii, so 3 AU in diameter. Some are saying 1.2 sort of time. So I kind of put it at 1.5. There's the Earth having a very bad day. Let's be absolutely genuine about this. It's not going to be a happy boy about being this close to the sun. I read some really cool articles about this earlier today, actually, just through accident, actually, talking about how the habitable zone, so the region in which liquid water can survive on the surface of planets, will just slowly move out as the sun expands into its red giant phase as well. Just simply, it is so much bigger. We are so much closer to it. Life on Earth would not be habitable way before we get to this big. And then the exciting point was that, let's say it gets to 2.4 AU, which is something I read today. By Earth, we're not happy.
Yeah, I guess I should point out when I said it cools slightly, it's still very hot. We're not going to be very happy about being near it.
Yes. Oh, yeah, you're completely right about cooling. It definitely cools down as it expands, but relative to our scale, not enough for it not to be possible. But there was a really interesting thing: is that some of the further out planets would now be inside the habitable zone. So maybe some of the ice moons of, say, like Europa, could melt and actually might be able to support liquid water. That could be really cool.
Yeah, I mean, those moons out, the Jovian and the Saturnian system are already some of the best, what we think are some of the best chances for life in our solar system. And actually, this cataclysmic change for our planet would actually be beneficial for those moons. So who knows? But the whole cycle of life could be started anew on a completely different planet because of this change in circumstances.
Yeah.
Just because it's not beneficial for us doesn't mean it's not beneficial for other planets.
Exactly. I mean, we won't be particularly happy about it, but by that point, too late. We can't argue.
I mean, me and you won't be here anymore, Andrew.
No,
so
no, I don't think I don't think this recording would survive either. So that's I just thought was a really nice thing to look at, of just like how big the sun, well, at some point, in about 5 billion years or so, will actually become. It will go through other phases. It will become a white dwarf, and there'll be planetary nebulae around it, but that's a little too hard to simulate, unfortunately. Cool. I like that one. That was a really cool question. Cheers for that. Let's have a look at what else we've got in that list. Oh, okay, that's definitely one I've not seen before, and I really want to try and answer it, and it's got a lot of likes. So I'm going to have to hand over to you, Josh, in a second, because it's going to take me a little while to throw this simulation together, but I'm seriously interested to see what happens. What would happen if we had two suns like in Star Wars? That's a great question. What would happen if we had two suns?
So if we had two suns, so again, these things are things that if we look up in the night sky using our powerful telescope, that we can see. So we don't have to take a stab in the dark just using numerics and theory. We can look at solar systems that have two suns, and they're normally called binary star systems. And there's a few different setups for them. One where you have a massive star and then a smaller star sort of orbiting around it. And another setup where you have two sort of smaller stars and they orbit around each other. You also have systems where you have more than two suns. You could have three. I think I've heard of four star systems before. I think we have found that planets can survive in these systems. Not as close to the suns as say like Mercury and Venus are, and that's because these, as you can imagine, these two massive objects orbiting each other, or one massive object orbiting another, actually causes quite a lot of gravitational disturbances. And what that acts to do means that the area where a planet can orbit is actually pushed further out in a stable orbit anyway, without being ejected from a system. So I think the sort of planets in Star Wars, you're talking like your Tatooines, your desert planets and planets like that, are probably not as feasible because you have this habitable zone pushed further out. I think they're more likely to be cold rather than hot. That being said, maybe you've got a massive sun which is really luminous, really hot, and you've got a much smaller protostar sort of orbiting it. Then maybe you will maybe a planet would be really hot, and depending on the angles of some of the orbits, then it could be quite close to the sun. So I see Andrew's managed to set up the simulation.
Yeah, I love this program. It's fantastic for this sort of stuff. So I've managed now take a solar system simulation. So this is again everything we're normally used to, and all I've done is popped a friendly neighborhood sun nearby, hopefully in somewhat of a stable orbit. So what is happening now? Every tick in the simulation time is 15 minutes, which roughly equates to every second is about 10 hours. So these things are shifting. They're moving incredibly fast around each other. I believe quite a lot of binary star systems do orbit each other really rapidly, right?
Yeah, they definitely do.
Yeah, it's quite impressive. So we're looking at it here. It's massive. Mercury is having a really bad time, which isn't too surprising, to be honest, because of just how much. So again, it's the sun. There's something called the barycenter of the universe, which is sugar. Come on,
Solar
barycenter of the solar system, not the universe. That's a really like we are the center of the universe thought there. Oh, Venus is not having a good day either. Which basically is where the solar system orbits around, and it's inside the sun, but it's not in the center of the sun. It's slightly shifted out because of Jupiter mostly. Now the orbiting center of our solar system is very different. It's going to be as a sort of partnering of these two suns. And they're going to make up such a massive percentage of the mass of the solar system. It's going to really ruin the orbits of pretty much every planet that's currently here. So this is not what happens if we formed with two suns. This is what happens if we just suddenly gained another sun. I just want to clarify. It could be stable, but
I think it's interesting to point out here that you've got two suns in there which are of a relatively similar mass.
Yeah.
So this is the second case that I was talking about, where these two stars dance around each other, rather than the first case I spoke about, where I had one massive star and a proto-star going around it. But you can see this really intricate dance that these two stars of a similar size go through. I suspect all of the planets are not going to have a good time.
No, well, having a look, I know I will at some point speed this up. The Earth's okay right now because the Earth isn't too close, but you can see, so the blue line, so the wiggle it's making is what's going to happen to it. And you can see it keeps changing because the stars keep changing. We've just lost Mercury, and Mars is next to be destroyed. So it's all going. Yeah, it's not. They're not having good days. What I'll do is I'll speed time up a little bit. I'll try. This is going to be pretty brutal. So Mars, these two are still dancing around each other. Mars and Earth are all being slowly pulled in. This is happening, I want to point out, over the course of a couple of days, right? This is not years, this is days. If there were two suns, it would ruin everything else. We're now so far away from the center, we'd have frozen to death by this point, I'd argue, as it keeps drifting.
We wouldn't be having a good time. We'd be very unhappy. I mean, there would be definitely gravitational effects as well, which probably we wouldn't like either.
I'm surprised that I love getting surprised. I'm surprised that they're processing out of the center. I wasn't expecting them to move forward so much in their dance.
I suspect that did you start the second star with some sort of
I gave it an orbit.
And I think the momentum you gave it to begin with has caused them to be ejected from a system.
Because that's what's happened now. So they've now basically just gone off.
Yeah.
they're gonna have a grand old time exploring our galaxy by themselves, leaving everything behind to die. So,
I suspect that the simulation is trying really hard to conserve the angular momentum, which is what's thrown them out.
And speeding up, it just couldn't cope. It's too difficult for calculation. But that was a really cool question. I wasn't expecting something like that, and I'm so happy that came up. That was really interesting to answer. Thank you for that one. I thoroughly enjoyed it. Cool. I hope that was enlightening and answered your question in some way of what would happen. Not good overall. Not good would be my conclusion there. Awesome. Right, what next? Let's have a little look. Oh, I like the backward planet one. We might come back to that in a little bit. We haven't got too much time left. All right, let's do the one that everybody always asks about in every show literally I've ever done. Someone's asked this question: what would happen if the sun became a black hole? Let's do that one.
I suspect that's because people are expecting us to say something like the Earth will be dragged into the center of the black hole. Yeah. And that'll be the end of it, and we'll get spaghettified, and it'll be really fun. Not for us, but for people like aliens. But I think I'm gonna have to disappoint people here slightly. So what the premise of this question I'm taking it is: you take our star and you compress it down, you go through your neutron degeneracy pressure, and you make a black hole.
Yeah,
so you have a black hole with the mass of our sun, but with the density of a black hole. And the simple answer is that it's not that interesting. The Earth's orbit wouldn't change because the thing that we are orbiting, the mass that we are orbiting, orbits have to do, the way that we work out orbits is to do with the mass of two bodies, and that's how they interact with each other. The mass hasn't changed, so the orbit will stay roughly the same. We won't be having a very good time because about 8.5 minutes after the sun becomes a black hole, we lose our source of energy. So we'll get cold pretty quickly. I read we have about 2 weeks until 2 weeks until we freeze because of basically the greenhouse effect. We've trapped so much heat. We've got about 2 weeks until we'd all freeze to death, which is actually quite a long time when you think about it. Well, I suspect we'd also get light for slightly longer than the 8.5 minutes, because there'll be light trapped near the event horizon, which will take longer to get to us because of gravitational effects.
I think that's a really good point. I thought of that before. So what I've done here, just for clarity, in the simulation here, I've just literally, there's my favorite button in all of simulations games ever, is the black hole button. Just make this a black hole, which I have done, and you can see that things are orbiting fairly gently. As Josh was pointing out, orbits are determined by two things. Mostly mass and distance of the thing. Our distance to the sun has not changed. The mass of the sun here has not changed, and therefore our orbit has not changed. Our gravitational pull hasn't changed, so we're still orbiting as per usual, as is everything else. They're all quite happily just spinning around this now very, very dead.
I think what people really want to know is I've just done it here, and maybe if I've got it wrong, one of our hand fact checkers can correct me. They want to know what the event horizon would be, and I think it's about 3 kilometers, so nowhere near 1 AU.
Oh yeah, it's tiny, isn't it?
Yeah, I've just used the Schwarzschild's radius to check it.
Oh, that's nice. Oh, that's good bit of maths there, good bit of actual simulation. But you can see very little, right? It's a remarkably dull answer, which is a shame, really, unlike a lot of space where it gets really exciting. But I thought I'd just take this opportunity whilst we're here to push another one of my favorite buttons in this. It's literally one of the coolest things I've ever seen. So actually, no, I'll open up a new one. It's sort of semi-linked. It's just a chance to talk about it whilst we're here. It's speed of light. So there's actually something really cool we can do. If I push this button here, it sends off a light pulse. So that ring there is actually light. We can visualize the speed of light. So this is how fast light travels in real time.
So there's an important definition to make here, which is the medium that the light is traveling in. Because when we say the speed of light, people assume we're talking about the universal speed limit which is the speed of light in a vacuum. So the fastest that electromagnetic radiation can move when we place it in a true vacuum, which is about 300,000 kilometers a second.
Yep, absolutely. Thank you for the clarification. It's a really good one. And you can see, it's shifting. But this also gives us a great way to show just how big our solar system actually is. That is light traveling right there. That is genuinely in the simulation right now, how fast light travels in real time. Remember, turning on torches and turning on a light switch, although there's a delay for that to turn on because the electrons and all that and the flow of the charge through the wire, the actual light bulb turning on for us looks instant. Light seems to travel instantly. It goes around the Earth. I think it's like something 7 times a second, something like that. It's remarkable, if not more. But you can see just how long it's taken to get to Mercury, and Mercury's the closest planet. If we sat here and waited it to get to the Earth, we'd be here for another 8 minutes or so. I just think this is a really lovely and quite rare opportunity to actually watch light move in real time, which is really cool.
I mean, I think the thing that illustrates how massive the distances are when we talk about space is we talk about how far away systems are in light years. So we literally take the fastest thing that we know of. Well, the fastest thing theoretically in the universe, light. I say theoretically. We haven't found anything that breaks it yet. So we're pretty sure. And even then, the closest star is still light years away from us. Traveling at the speed of light, the fastest we could go in the universe, it would still take us years to get to just our neighboring star system. So, the distances that we're used to thinking about are just so staggeringly different to astronomical distances.
Yeah, absolutely.
It's really hard to get your head around how far away things are from each other.
Cool. This is good fun. I'm really enjoying this. I thought I might. This is really fun. All right, let's have a look at some other ones, shall we? We've got time for a few more. I did say I'd do that, but that's going to take me a little while to figure out. Because there's this one about the order of the planets backwards. I actually want to know what would happen there, but to set them all up in order, I will just need. Actually, I'll get our researchers to help us. Researchers, hello, my lovely team. Could you, for me, get all the distances in AU, or no, let's do it in AU because it's shorter, for all the planets for me. Just jot down in our little private thing. Mercury, it's AU, and then just down the whole list so that I can then quickly pop all the ones in the right place in just a moment. Thank you. That'd be really, really helpful. Cool. As they do that, we'll answer another one, and then I can go back and start working on that simulation. Space rubbish. One we got in earlier. What would happen if space rubbish kept piling up?
So
That's a cool one.
Space rubbish is actually a real issue. It's so much of an issue that this is something that space agencies are thinking about how to tackle. They're not thinking about how to tackle it in 100 years. They're thinking about how to start tackling it now. And the reason for that is space rubbish is really dangerous. Stuff in space goes really fast. So like you hear about like flecks of paint hitting the International Space Station. So these tiny flecks of paint, because they're orbiting around the Earth, they get sped up to massive speeds, you know, like thousands of kilometers per second, something that couldn't happen on Earth. So these tiny flecks of rubbish, when they hit a satellite or something like the International Space Station, cause these massive dents in this big thick paneling. So if a fleck of paint can do that, imagine, you know, you have a little bit of a booster rocket, which is being has managed to somehow make it into a stable orbit, being sped up around our planet, and you see that as this rubbish starts to pile up, it starts to pose a real threat to space missions. And as we think, you know, we've got the Artemis project coming up from NASA, where we're starting to think about sending people back to the moon. That project leads to supposedly to a moon base, which we're going to then use to launch people to Mars. But all of this relies on us being able to get stuff from the Earth up into space in the first place. And if we can't do that because there's lots of rubbish floating around at these high velocities, taking satellites, you know, damaging satellites, damaging space shuttles, then it does start to pose a real issue. Luckily, the big part, most of the time, the big pieces of rubbish, like your boosters, which are left, aren't left in a stable orbit, so they start to fall back down towards the Earth. Unfortunately for us, the Earth has an atmosphere, which we use to breathe, but also provides resistance as this stuff falls back into our atmosphere, makes it really hot and essentially burns it up. But for these smaller bits of rubbish that I was talking about, obviously flecks of paint are probably too small for us to track. I think is it the Australian government who've got this really cool program where they're talking about using lasers to heat one side of a rubbish to change its orbit from a stable orbit to an unstable orbit, so it will burn up in our atmosphere. NASA, I'm sure I saw something about space nets to start to clear this stuff up. So yeah, it's something that governments are thinking about now, and it's something that could be oh wow.
So this is what happens if basically we really mess up and have a lot of space debris. So the idea is that as one thing hits another, it debrises and splatters out. If that hits the next thing, that debrises and splatters out. As that hits the next thing, that debrises and splatters out. And that keeps happening. So literally collision, boom, collision, boom, collision, boom, until eventually it's impossible for anything to leave Earth's orbit anymore, because there's just debris everywhere. There's a term, I can't quite remember the term is called, but it's a really dangerous point, and we're rapidly heading towards it.
I also can't remember the term.
I was really hoping you were like, oh yes, Andrew, it's this one. But this is just obviously these are completely arbitrary lines, but hopefully you're seeing just the scale of like what happens if I ignore the fact it says Ceres. What happens if I just choose a couple of objects and blow them up? You can just see the splintering and how much of a problem that's going to become. And that's, I think, about 5 or 6 objects splattered into about 10 different pieces. And that's what's being tracked here. And already it's enough of a simulation to really hate me. So yeah, pretty cool stuff there.
Yeah, space rubbish is an issue of the future, but not of the far future, of the near future.
yeah. Absolutely. All right. What time is it? Oh, we've got time for not a huge amount more. We could do. I really want to do that really cool one about the backwards, but it's just gonna take ages for me to put it together. I might start trying to do that. In the meantime, then, as I start desperately trying to put that one together, shall we do what happens if the sun disappears?
Yeah, so this is perhaps what I was alluding to earlier, where I was talking about the sun just being completely removed. So as we spoke about earlier with the black hole and the masses, there are 2 things that control planetary orbits, which is essentially the distance away from the star and the 2 masses. But what you've got here is the mass being completely removed. So what would happen is the trajectory. So you imagine the Earth is going around in a circle, and if you think about that motion, it's because it's falling towards the star whilst shooting at tangential velocity to it as well. And if you remove that thing pulling it towards the star, then we just shoot out in the direction that we were traveling, tangential to the, essentially in a straight line away from the star. Think of it roughly like that. And it wouldn't just be us that did that, it would be all of the planets that did that. So if we start to think about the effects on our planet, obviously, like I said before, 8.5 minutes we wouldn't notice. And when I say for 8.5 minutes we wouldn't notice, I don't just mean in terms of we wouldn't notice because the light would still be there. It would actually take the effects of the gravitational effects of the star being completely removed 8.5 minutes to meters, because gravitational effects, just like every other effect in the universe, only has a maximum velocity of the speed of light. So both gravitationally and in terms of the photons coming which heat our planet, it would take about 8.5 minutes, 8 minutes, 8.5 minutes for us to notice anything had changed. After that point, obviously, then we're starting to fly away in a straight line. We're no longer orbiting in a circle. We're all of the planets in the solar system would be sent off in a straight line, starting to head on a journey through our local cluster. Earth wouldn't be very happy because we obviously wouldn't have a source of light and heat anymore. If we were to look up in the night sky, the moon would pretty much disappear straight away. It would continue to follow us because the moon orbits our planet and not the sun, but we wouldn't be able to see it anymore because the way that we see moonlight is by it's essentially reflected sunlight. The stars would start to shift as well because our perspective would start to shift. So the planets to begin with might look like they're staying in the same place because they are relative to us, but the background stars, the constellations, would start to shift their positions, and eventually we'd stop being able to see the other planets as well because the way that we see them is by them reflecting starlight back to us. So we'd be left on this sort of cold voyage heading in a singular direction through the cosmos, not very happy because we'd be very cold and dark.
And we'll start talking about this really cool final question. Team here, are we okay with that?
Me, interestingly, I see that we've included Pluto as a planet. I thought we got rid of that one. I thought we were sick of it.
I'm deaf. Pluto is not on my system. So this is a proper hypothetical, Josh, because I don't think there's any reason that we would actually understand what's going to happen here at all. This is completely unknown to me, at least. I
mean, the thing I can sort of think about is a bit of planetary migration theory. So this is
go on.
When we think about the way that the planets were in the formation of the solar system, there is a lot of evidence that where we see the planets today were not where the planets were actually formed. And the reason for that is when we look at what makes up the planets, obviously Earth, Venus, Mars, Mercury are very rocky. But if you think about what our sun's made of, which is the lighter elements, so we're talking helium and hydrogen, and then we take a look at our gas giants, so Jupiter and Saturn, we find that they're also made of mainly lighter materials, so hydrogen and helium. So there's a lot of thinking around whether they actually formed closer to the sun, and we, as more rocky planets, formed further away. And then at some point, due to the gravitational dance of dust coming together to form big gravitational masses, there was some sort of it would have been climactic at the time, but obviously doesn't affect us anymore. We're doing pretty well. Where the gas giants moved outwards and we moved inwards. Luckily for us, they did move outwards because Jupiter is our savior in the solar system, protecting us from asteroids and meteorites which come in. So we're grateful it is where it is. But yeah, there has been. So this is the thing I can sort of think about when we talk about this. So maybe there'll be some movement of the giant planets. So Neptune will be the closest planet to the sun. Neptune and Uranus are both these very strange planets that we don't actually know that much about, called ice giants. But as the name implies, they are giant planets still. They're a lot bigger than Earth. Then we'll have Saturn and Jupiter, our gas giants. So maybe thinking back to what I was saying about migration before, maybe they'll start to move outwards, or maybe because the orbit won't be stable, they'll actually start to move inwards because there's these two large masses much closer to the sun.
Whew. Okay.
So let's have a look.
Let's have a look. So genuinely, I've never tried this before, as is evidenced by how much we scrambled to get this together. Again, thank you so much, Pascal, for giving those numbers. Otherwise, this would have just been impossible. What I have done is unrealistically put them vaguely in a line, but the distances are so large, I don't think it's going to really make much difference. I've not pushed play yet, so let's find out what happens. I don't know. I would be surprised if too much is different, really, is my point. I think the distances are still going to be large enough that we're not going to see anything too radical. Maybe. I don't know.
I mean, everything I spoke about happened in astronomical timescales. So we're talking, millions of years for these things to move. They're not moving overnight.
No, I don't think so. I think really what we're going to see is still. So these have all been put. So Neptune is where Mercury should be, right? Neptune is where Mercury, Uranus, Saturn. You can sort of just see everything kind of feels right in this bottom region, and then we start having the big jumps. It's very weird to see Earth this far out. So Earth, for reference, is now where Saturn is, just to clarify. But realistically, as I kind of guessed would happen, things are fairly stable. And I think that just goes to show how much of the orbits of the planets is exclusively dependent upon the sun. The sun making up 99.9% of the mass of the solar system. So its gravitational pull is so much stronger than the pull of any other planets that they're not really going to interfere with one another. And their orbits are going to stay remarkably stable. Obviously, this is a simulation. That the orbits aren't perfect circles, but I could sit and make them the correct ellipticals as well. I have that ability, but that would just take us hours to go through. But yeah, I think this is a great tool to show that realistically our solar system is a really, really stable place. What do you think, Josh?
Yeah, I'm sorry. I'm peering at my screen, looking at the orbits. Yeah, I mean, I don't see any reason why there should be any sort of dramatic throwing of one planet out of the solar system. Like you say, the sun makes up 99.9% of the mass in our system. So, I mean, they are remarkably stable. I will say.
Yeah, I mean, we can see the sun is processing a slight bit, which is normal anyway, right? We know the sun moves about on its orbit, but that will now be greater, right? Because of the heaviest planets are now closest to it.
Yeah, I mean,
so Neptune, Jupiter, Uranus are going to be pulling it around a little bit, and you can sort of see that here, right? We can see it being pulled backwards and forwards a bit.
Yeah, I mean, even where Jupiter is now, it causes a slight precession of the sun.
Yeah.
So being closer isn't going to do it any favors.
And we can actually see how that's obviously, again, this is just a simulation. We've got very stable orbits here, but you can really see, look how that's giving us quite a shift to the left and then back and then left again, which is really quite impressive. Obviously, when I say little shift, these are massive changes.
Yeah, if the sun started doing this in real life, we'd be, start right. Get your telescopes out, folks. You could be the next big scientist.
Yeah, exactly. This would be quite a change. But I think that's really interesting. I kind of semi wasn't expecting that. But obviously that's processing forwards. It's dragging everything with it as well. Naturally out by Earth, apart from the fact we'd all be frozen to death, I don't think you notice too much of a change there. That's really cool. Well, I didn't know what was going to happen. Josh didn't know what was going to happen. And that was the whole point of this show. We were here to test out your hypothetical questions. So again, all the questions submitted to us weren't ones that we invented ourselves. They're ones that you all submitted. A couple of them I chose from the Eventbrite list. The vast majority, obviously, we just picked up in the show here today. I just want to say thank you to everybody who made this show possible today, and we'll go through them in order. So first of all, it's Josh, who was naturally sitting and chatting away with me today, who did a great job at discussing all these interesting topics. So thank you so much, Josh.
Thank you. Thanks, Andrew. Thanks everyone who came and listened to me whittle on about some space sciencey stuff. I've had a great time personally, just chatting some space science. So
it's been good fun.
Questions are fun.
Next, just a big thank you as well to Diego, although not as Pascal, working really hard behind the scenes. Thank you so much, Diego. Cheers, man. And finally, she's been here pretty much every week asking all the questions and been a fantastic support to the show. A massive, massive thank you to Pascal. Cheers. Oh, you're an absolute superstar. Thank you for watching, and I hope you enjoyed learning a little more about our amazing universe. Our team from Lancaster University also runs shows for schools, community groups and more, both in person with our portable inflatable planetarium and online. But any in-person events are subject to current COVID restrictions. If you're a teacher, community group leader or part of a similar educational organisation, please do get in touch. We're particularly keen to make connections with those in our region of Lancashire and Cumbria, but we'd love to hear from you wherever you are. But for now, take care and keep learning more about the amazing wonders of our night sky. Thank you.